start in the radiative part, so we are stably stratified first. And so I see the surface starting to be wavy anyway. I see an increase of density. So I succeeded not to have some, you see, instability starting. I have quite a nice profile. My problem is I don't understand why it's not propagating to the center of the star. What we were waiting is simply kind of damping by this kind of wave. So we see some effect on the velocity field and on the pressure, but it seems that it's impossible to really nicely propagate through to the center of the star, especially when the internal rotation profile is almost solid rotation in the radiative part for massive stars. It's right that the velocity field is smaller, and it seems to be to create more instabilities that really involving normal behavior. So we don't understand why it doesn't propagate. It seems to be linked to the cane.
But I mean, do you think that this is a numerical problem?
Yeah, I think it's a numerical.
Or do you think that it's a physical problem? If you increase the resolution, do you
no,
get the same problem?
It's worse.
It's an important issue that needs to be clarified first. What is the mesh Reynolds number? So that needs to be defined first of all. So let's define it or write it first of all like this.
So we're not turbulent, but we have.
Yeah, but it doesn't have to do with turbulence. The Reynolds number does exist when the velocity.
We have a 600 on a unit distance. We have a 600 meshes, and the velocity field is CGS is 10 minus 5.
10 to the minus 5. What is the mesh spacing?
We have on a unit distance, it's on one unit, we have 600.
Yes. And what's the viscosity?
Good question. I would say we are the order of unity, I guess. We are not expecting
unity. Yeah?
Yes, we are not ideal. We are in evolution, so we are
in CGS unit is 0.1 unity.
Yes, it's
right. Oh, the velocity is 6 minus 5.
In CGS, so 10 minus plus.
Oh, but there's other velocities of course. That means sound speeds, sound waves, for example. They have very high velocities again.
We don't calculate sound.
But I mean, isn't that terribly viscous then, if you have?
No. These velocities are just extremely slow, but it's compressible. You have to be compressible.
Yes. Yeah.
And if you are compressible, you have also to consider the sound speed. And then the sound speed that will be on the order of 10 to the 6th.
Yeah, the
6th, perhaps. 10 to the 1st.
That is the definition of the mesh Reynolds number?
That's the definition.
What you put in the sound speed. Or the
it's
maximum, whatever. With the velocity.
Yes. So the criterion is probably dependent. There are cases when 30 is okay still, but there's also cases where 30 is far too big and 0.5 is okay. So for example, if you have a shock, then you of course have to go much below this. But it's hardly possible to go much above this.
I have to see the value.
Yeah, but I mean, you cannot never eliminate the waves. The waves have a possibility to exist, and once they do have a possibility to exist, the code cannot sort them correctly anymore. If the corresponding Reynolds number for sound is too small. I mean, the Reynolds number for sound can be much higher than perhaps even 30. But certainly, if you always have to have even much more than 300, and all bets are off. So I think you have to increase this one and see whether you can get the problem under control by increasing the viscosity.
So it's very slow. It's 10 minus 5 centimeters per second. CGS it's extremely slow. So
but the sound speed is very high.
Yes, I have to see this.
Another thing is, often problems in astrophysics are simply not possible to do in the way that one would like them to do. So that means if the sound speed is extremely high, you either have to eliminate the sound waves. That means you have to do an incompressible code or an elastic one. Then you can get rid of this.
And I think that's the only way you can do 10 to
But
the
if
minus
you have-
5 if you have a sound speed of 10 to the 6.
But even then you have ground bass frequencies. Say stratified. And their speed is almost comparable to sound waves. So you better then do an implicit solver. And none of these two options we can do. So one possibility is to not really solve the star as it realistic would be in a realistic setting, but to solve a simpler star, which has a smaller temperature and therefore a smaller sound speed. And if the problem does not depend on the value of the sound speed, then of course it doesn't matter how big the sound speed is. If the problem does depend on the sound speed, maybe it depends on the sound speed in a fairly logical way that you can understand. So if, for example, your result is 10 times too big, just because the sound speed is 10 times too big, you would know that, okay, if it's now 100 times bigger, then this one would, the other factor would also be 100 times bigger. So you can use a code to extrapolate towards the sound once you understand the scale.
Okay, I'm suspecting just I was thinking the sound speed is a little bit higher than this one. It's 10 exponential and something like this.
So 7, yeah?
Yes.
10 to the 7, yes.
Yes, yes.
So it's in any case extremely bad. So 10 to the 7 divided by 10 to the third means 10 to the fourth. So that's way too big. I hope that these illustrations are hopefully of some more general educational character, so that's why I spent some effort in explaining this. But I think it's a general, it's an important issue to realize that the code is, of course, not a black box where you can just force things to work, which physically have no way of working, or physically or computationally. The Reynolds number, there has to be enough resolution, simply.
Yes.
And this is, this is what is expressed by this criterion. If you really say you want to do astrophysics, that's just very small, and this corresponding thing is very large, then this formula tells you have to use several million mesh points, or maybe a billion mesh points. That's what the formula tells you. And then you say, okay, that's what I have to do, and I apply for my grant time.
Yes, but I agree, but in fact it's an evolutionary code, so people normally don't do hydros, and that's the reason why I say we are probably at the limit of the code, because we want to do hydro. I see the problems, I see there are problems, and there are miracles.
So that was the point now about the hyperdiffusivity. Yes.
Sorry. Regarding the upwinding speed, what I found problematic is that if you replace the central advection term in the continuity equation that is upwinded term, then the whole equation actually turns into, it's not a conservation equation anymore. And I actually had very significant mass loss in a few of my simulations.
Can you write this down?
Which wasn't very popular among the people I work with.
That's conditioning.
Yeah. And I try to find a way to make it actually conservative, but I failed to do so. So if you have the continuity equation, yeah, that's conservative. Okay, that means that d rho dt plus u dot grad rho plus rho diffu, still conservative. But now if you replace u dot grad rho by u dot grad rho plus, and I think it's grid spacing to the fifth u over 60, and then a sigma order operator here, then u is position dependent.
It's the sigma operator of the rho.
Right. Sorry. Yeah. So and then you insert this here, and then you can see that you actually have d rho dt plus centered divergence. And that equation is perfectly, like, numerically conservative up to machine precision. But then you get this term on the right-hand side.
Yes, that's a price.
Which is, so you get minus something that is proportional to u, and delta 6. So, and you cannot drag this out. You cannot write that as a divergence.
That's because you entered there, right?
Right, because u is position dependent.
If you didn't enter, you could drag it out as a divergence.
If I would?
If you didn't enter, you could write.
If I didn't enter u?
If you didn't enter, if there wasn't no you, then you could write the sixth derivative as a divergence.
Right, yeah, that's what I'm actually doing. So I'm using actually just hyperviscosity for the continuity equation. So they have a constant coefficient here. But upwinding in my shear and box simulations, they had very significant mass loss. That was extremely.
And that's the problem. That's the part to play.
And it gets even worse if you do logarithmic. If you replace the logarithmic advection term with the upwinding term, with the upwinding version, then it gets even worse because you have a. I can write it down, but you get, if you would do this correctly, I guess you can even do that somehow by adding an extra term, but if you do the logarithmic advection term, you can forget about it to begin with. It's completely... I think you cannot even do it with a constant. Yeah, exactly, then the continuity equation becomes non-conservative even for a constant coefficient in front of the hyper derivative.
Well, that's
I think.
What was the last thing?
If you evolve in terms of logarithmic density and replace the central advection term by an upwinded advection term.
No, that will never work.
Yeah, but then even for a constant coefficient, you don't have a conservation law anymore.
No, if you said number 6 of the log road.
Yeah.
No, that's not conservative.
Yeah, that's not conservative in any event, right?
One thing which is possible is to map log row to row and then do the sixth derivative and then take it back and divide by row. Or it's not really tested or anything.
But I think even that would be non-conservative, actually.
Yeah. I think analytically that would be conservative, but adding up those different terms might not be.
But if you do that, then you actually don't have. I mean, that wouldn't actually be the same as the hyperderivative of log row, right? That would be something different, yeah. Hyperderivative of row divided by the row. Yeah, so that's a bit problematic, and I haven't found a way to actually remedy this, except for using non-logarithmic density under constant, and just ordinary constant hyperdiffusivity. But on the other hand, in my sunspot, in my convection runs, I don't have very significant mass loss at all when I use that. So, I mean, it really depends, I guess. But it's something to watch out for, I guess.
And then it, of course, it depends a lot on resolution. I mean, there's delta x to the fifth there.
Mm.
So, if you increase resolution, that makes it less different.
And the advection also. If you have a strong advection, you have and you see that. You see that sometimes you can have a large mass loss in the box.
That was for MRI or what?
Yeah.
Because for MRI we have a strong shear, of course, simply from the shearing motion.
Mm-hmm.
Is that maybe the main cause of this?
It's a systematic mass loss. I mean, it's never a mass gain.
Yeah, I've also seen that, especially with logarithmic density.
And it can be in starting the box simulation. Can be a big problem because when we impose, in fact, the velocity tends to 0 at the surface. So we have a strong effect on the border. The velocity tends to 0, so we have a strong velocity gradient. And then winding should be very efficient in this case. And then we have large mass loss in starting box simulation, much more larger than in Cartesian. Cartesian box.
Because you have larger velocities.
And, no, because the artificial boundary condition at the surface means that the velocity is 0 there. Because we damp the velocity artificially at the top of the domain, at the surface of the star.
And in this case, the mass loss is higher than than convection in a box where the velocity is not zero at the top. That's the vertical velocity is zero, but the horizontal one is not zero. And then the velocity gradients are not so large in a box than in a star in a box. And I experienced that, as Toby said, in star in a box simulation, the mass loss is higher than in a box, in a convection in a box. And it can be maybe a problem for a very long run, because you lose mass in your domain, in a computational domain.
I mean, the total mass of the average density is certainly a quantity to monitor. And there are cases where this is not an issue, like for the star in a box runs that I did, the mass drifted very little. And I'm tempted to say that if you really get significant mass loss due to that, then your simulation is under-resolved. But I think that's too general a statement. I guess it really depends on
Indeed,
what
I
you're
mean, that of course makes sense in principle, the statement. So, the Evan conservative code, there are factors which are conditioned due to the particular terms that we are deliberately putting in, like hyperdiffusion. They clearly break conservation law. We hope that those terms are small. If you're telling us that they are actually large, then that means you are relying to a very large extent on these numerical factors to help you out in diffusing the high wave number stuff. So that
well, okay, but I mean, there's no diffusion in from the mass diffusion in the first place, right? I mean, what is there to rely on?
Oh.
Well, there's no hyperdiffusion.
Yeah, maybe a short tutorial-like thing again. I mean, we in principle need, of course, diffusion, even in the continuity equation or in any evolution equation. That has to do with a phase error in the discretization scheme. So each scheme has two different errors. There's first of all we have to do with temporal derivatives and we have to do with spatial derivatives. The temporal discretization can give rise to amplitude errors, and this one can lead to phase errors. And so, for example, if you do an Euler scheme, you just do an advection in an Euler scheme, you will find that your sine wave will grow in amplitude steadily. That means the first order scheme has a positive amplitude error. The amplitude will increase with time. It's an anti-diffusive error. The second order scheme, anybody knows that? Positive or negative? Yes. And third one? No. That one is negative. And the fourth one is also negative, and then it's positive again.
I thought we had a very little.
Yeah, we have a very little one. First of all, it's negative, and it's also very little because it's third order.
That's why we need more distribution. I mean, if that was very negative, we wouldn't need this loss here.
We would need because this is a diffusive error already.
Yeah, so I'm saying if this was very negative, we wouldn't need it.
That's correct, yes. Yes.
So we would still have a large amplitude error, just not a lethal one.
It would be uncontrolled.
Yes. Okay, so then we have the phase errors. So that means the following: if you have the signal will propagate, the phase error means it has the wrong amplitude. Amplitude error means it has the wrong amplitude. Phase error means it will lag behind. Typically, it can also advance, of course. So that means that's what happens. Of course, this depends on how many mesh points you have. So if you have a sine wave with 8 mesh points, then there will be a certain error which you will maybe see. But if you have a wave number with a very high frequency, the error will be much, much larger. Now, if you have then a signal which is a jump, for example, a function of this form, this of course corresponds to a superposition of different Fourier modes. And then what you will have is that this one, because this one is very resolved, it will not field any error. This one will field a very large error. So that means after some time when this one has propagated, the large wave number stuff will have the right amplitude, the right phase, but the high amplitude stuff will be behind. So you will see in these trails you will see wiggles here. And that's just because those ones are not fast enough, they can't keep up. And this we don't want. And therefore we always need explicit diffusion, even for the continuity equation. Even though it's not physically anything, but we do need it numerically.
Could you say briefly what happens when the code afterwards crashes? And I mean, I understand wiggles is a bad thing. We often see the code crashing, but that must come from the wiggles first, right? What actually happens when you go from wiggle to the times that getting to zero and code crash?
And then I have to work out, typically one can interpret these things in terms of physics. There can be an instability, of course, which is caused by these high wave numbers.
But I don't understand, because we only have negative amplitude error. Why does the code always end up crashing with a very high velocity and very low time step?
I mean, we have non-linearities, and then
what?
Non-linearities, and they can lead to all sorts of problems if you have bad things going on small scale.
So it's not the linear part of the equation that really did crash. It's something with the equation.
I guess there probably are scenarios where you can really figure this out. But you're right. If we use third order and we just do advection, then I don't see how. If the time step is small enough, then I don't see how you would get exponential growth in the linear.
But that's in the linear phase. Yes.
I mean, maybe that is something one should check whether. I mean, you can easily distinguish between linear and nonlinear by looking at the temporal behavior. If the temporal behavior is exponential, then you're right, we have a linear numerical instability. But most likely it actually really is never exponential in numerical instability.
Typical crash is everything is fine and then boom.
Then it goes really fast, right? It's not exponential. It's not faster than that. So I think it's probably true what Hoffman says, that we are really talking about nonlinear.
As soon as you have this sort of thing in the velocity, you have all sorts of nasty nonlinearities and steepening of velocity profiles, and that can crash easier.
And it also doesn't conserve at the same time. Or often the crash is accompanied by the mean density going to infinity or to zero. So you must somehow break the conservative form of the equation also.
I mean, the errors are, of course, dependent on the actual various function.
I mean, the nonlinear terms are responsible for actually propagating the small scale error to larger scales, and then that's when it goes really bad, probably.
Either that way or maybe the other direction as well. I'm not sure what.
Okay.
You know, small scale. It sounds more plausible to me that the small scales blow up. Yes. Because they are less limited in a sense.
But maybe if you do a peasant code table, we could have a section on what happens when the code crashes.
Crashes?
Because I mean, it's not so obvious, right?
A small appendix about what happens if it doesn't crash.
And subwinning is a crucial point for me, because we put a lot of time of upwinning flag through, and but we don't know exactly what happened in reality, the computational in the domain, you know. And it was, for me, I discovered that when I used symmetrical coordinate, I realized that without upwinning, the results are completely false. After some time step, you have a lot of wiggles in the domain. And
but you could always get away by adding more diffusion.
yes, you can. Yeah, but.
I mean, by the way, we should also be very careful about making sure we are talking about a real numerical problem, not just a coding error.
It's not a coding error, no. Because in cylindrical coordinate, coding is not coded actually. It's not coded. Then,
Sure.
so you
Yeah,
are
yeah,
doing something without a reading, and you realize that without a reading, a convection between in a cylindrical shell leads to completely false results on the flux, on entropy, and so on. And then we realize
This
that
can't be true. I mean, we have been working more or less okay with just ordinary.
a strong convection with a strongly nonlinear convection with a high real
And
number.
that comes from the density equation, say, or comes from the continuity equation problem?
Because of continuity. The entropy is not so crucial, I think.
Well, and entropy is then.
Yes, it does.
But this should really be, even without uploading, this should be resolution dependent.
Sure.
But maybe if you have possible, I'm just guessing now, if you have a strong stratification, if you have many orders of magnitude in density between the center and the outside region, probably the problem can also get worse due to that.
I mean, I guess it depends a bit on whether you have a systematic, I mean, the error is systematic that you introduced by the non-conservative term in the continuity equation. I mean, if the mass stays more or less constant, it could be that the local mass loss is sort of, or gain is the same, but it sort of balances out. But if you have a systematic loss, then you actually see it, and it becomes a big problem. And maybe, I don't know, maybe this such systematic error can be introduced by having shear or stratification or some anisotropy.
I mean, stratification, strong position, strong variation with position certainly makes the violation of the conservation problem larger.
Are you talking about a stratified problem?
Well, I never had really issues in the stratified problem.
So that's not an issue. So it's
But the stratified models crash at the upper or the
Yes.
boundaries constantly. It may be related to this also overall.
But by the way, Toby did not use in many cases an extent of the box which was large enough. That was a suggestion by Stone, of course, some time ago already, who said that one should really make the box 5 scale heights big.
Doesn't matter. And 5 scale height, anything.
In any event, that's just something to remedy a boundary condition that is bogus to begin with. I mean, you just.
Yeah, but the field is at least much bigger.
Yeah, sure. But I mean.
But I have tried this Parker stability stuff, where I have 5, 10 stratification scale heights. And it doesn't matter how big I make the box, how small, it always crashes exactly at the boundary. There's a little window forming there. In the density first. Density goes to 0, and the logic goes to infinity. And even though the code can handle Mach 10 flow everywhere at the boundary, just at the boundary it crashes.
Always. It's very tired.
That's periodic in X and Y.
Yeah, that shear period with shear. Without shear was a bit even 5, 10 scale height with shear it goes to.
Well, what's going on in the box if you don't have shear? I mean, with convection and so.
I was just having Parker stability instead of just a stratified medium power arcs being exposed. And this was fine.
I mean, she constantly pumps energy or signal from large scale to small scale. And certainly.
So one thing I have success with now was put the vertical velocity at identical 0 in the boundaries. Don't extrapolate or anything, just put it at 0. Then it seems to not crash anymore.
Oh yes, what else should be?
I tried the A, which is reflecting.
Wait a minute, you said H, velocity to 0 everywhere in the ghost zone, including the last active zone.
Yeah, that's what you're saying?
Yeah.
Yeah, that's interesting by the way. I know that.
That seems to be stable. I'm not saying it's physical, but.
And it's interesting. There's a guy called Javier Sanchez Salcedo who was working with me in Newcastle, and Wolfgang knows him. Wolfgang is here, yes. And he actually introduced this at one point in a former version of the code, not the console code, and he used this for just incredible problems, and it works very well. So that's a very, very nice way of dealing with these problems.
Well, my experience with both A and S and A2 is that it fetches no.
Yeah.
And it's often when there's outflow, I notice. It's usually something is not working, you just kind of trying to escape from the box. And then when it's trying to get out of the box, it starts wiggling and going. So,
Yes. And so everyone takes care of those things.
yeah, I mean, Lab's ultimate solution is to do border quenching, which means that you you kill the D by T term and near on this kind of the nuclear bomb.
But that's easy to interpret than what you do.
Is it easier to interpret the border quenching? What is the physical effect?
There's two different interpretations. If you say you just, what we're talking about is